Hello, welcome to our virtual lesson for Unit 5.4, Chapter 5.1 through 5.3. Chapter 5 is regarding populations, and the big idea for this, what factors contribute to changes in populations. Okay, Section 1, how populations grow. Our objectives here, list the characteristics used to describe a population, identify factors that affect population growth, describe exponential growth, describe logistic growth. And these will be our vocabulary words: age structure, immigration, emigration, exponential growth, logistic growth, and carrying capacity. Okay, geographic range. Imagine where on the globe you expect to find this species. Where on that continent, perhaps, you expect to find that species. Are they close to the coast? Are they in the mountains? Density and distribution, then, is the next bullet point. The more individuals are packed into an area, the denser the population. These penguins, if you put 10 more of them in there, that would be an increase in their density. And the distribution, well, how are they clustered together? Are they uniformly spaced? We'll learn about that on a coming slide just around the corner. Next bullet point, growth rate. Okay, well, how fast is this population changing over the years? Is it growing so fast that it's doubling each year? Or is there a limited number of individuals that tend to be added on each year? Is it starting to cut back in its growth, or is it leveled off at a certain point? Then lastly, age structure. Are they dominated by adults? Are they dominated by youths that are just newly born and have a lower survivorship rate? These are the factors that can be used to describe populations. And the geographic range is the area inhabited by that population. Now, within that area inhabited by the population, the geographic range, there are three overall strategies of distribution. Notice the plants in the upper left, their pollen and their seeds are distributed by wind. Well, not all of them, I shouldn't say that generically, but many of them are, and overall plants, they're randomly distributed. It's not like they decide where to go. It's so many factors involved, whether it's spread by wind, animals, water. It's really a random factor where they end up being deposited and where they grow. The penguins, they're competing with each other, but they're also a group of social animals, and they interact in many ways. They keep each other uniformly spaced apart. And then the fish, they school together in that group, and it protects them. It's a good strategy for them. So these are lining up with the visuals. The plants, they have a random distribution. The penguins, they have a uniform distribution. And the fish, they have a clumped distribution. The growth rate. Okay, so if a growth rate is 0, then the population is going unchanged. There are other, other calculations in sciences where maybe you're comparing to the number 1. Greater than 1 would mean one thing, less than 1 would mean the other thing. But in this case, we're comparing it to 0. So if the growth rate is 0, that population is not changing. If the growth rate is greater than 0, well, the population is growing. And if the growth rate is less than 0, the population is decreasing. Take a look at these 4 factors that all influence a population. The 2 that add to the number of individuals in a population are births and immigration in. Think immigration, I for in, coming in, adding to the population. Since births and immigrations both add to the population, notice that equation on the left, change in population, has in parentheses B plus I, because these are both factors, birth and immigration, that increase the population. Deaths and emigration, think E for exit, E for emigration. Exiting is emigration, leaving the population. That and deaths both decrease the number of individuals in that population. And so if you add up all the deaths and all the emigration out, that overall is what you need to subtract from the births and immigration that both increase the population. And this is how you can calculate the change in population from year to year. Now, how a population changes from year to year is what's being addressed here. Bacteria or elephants. We have 2 extremes size-wise, but either one can go through exponential growth, but on different timescales. Exponential growth means that they're growing very, very rapidly. Perhaps the population is growing by 1.5 times its current level every time you check in on the population. For bacteria, maybe that's just a matter of hours, or less than even an hour. For elephants, it's obviously a much longer time. I want to point out though that this is not very realistic. Exponential growth is only going to go on for a short term. Imagine the bacteria. They're going to run out of space if you grow them in a petri dish. You can feed them all the food they want, but they're eventually going to run out of space in that limited size petri dish. So there's always going to be a factor that limits how much they could, how long they can continue growing exponentially. It's only under ideal conditions with unlimited resources, very unrealistic. Only under those conditions can a population grow exponentially. More realistic is logistic growth. Logistic growth has 3 phases. The phase of rapid growth, phase 1, the phase where it's starting to level off and the population is still growing but not nearly as rapidly as it had in the past, that's phase 2. And then the carrying capacity, that's the level that the population is expected to remain at and fluctuate up and down around that level. But phase 3 is when the population is maintaining a relatively steady level influenced by its carrying capacity. All right, pause for a moment and try these questions on your own. You had a chance to answer these independently. Question number 1, 10 individuals per square hectare. That's a description of population density. Number 2, when resources are limited, a population will grow logistically. And realize that that's the only realistic way that populations do grow. Exponential growth only happens over a relatively short period of time. And then 3, when growth is greater than 0, the population is growing. Section 2 is discussing the limits to population growth. Our objectives here, to identify factors that determine the carrying capacity, to identify the limiting factors that depend on population density, to identify the limiting factors that do not depend on population density. Our vocabulary words here, limiting factor, density-dependent limiting factor, and density-independent limiting factor. Now, in this diagram, these are all the limiting factors that can keep a population size in check, keep it from continuing to grow exponentially. The two that are further to the right, natural disaster and unusual weather, these are both natural phenomena that are abiotic, not caused by living things. Abiotic means not having to do with living things. These abiotic events, these are going to be limiting factors that are not influenced by population density. No matter how dense a population is, if you burn down a forest, nothing is going to live in those areas that were just burned down, or at least it's going to disrupt it. And it'll disrupt it just as much if it was originally a dense population there or a sparse population there. So weather and natural disasters, those are density independent factors. The other 3 factors that we see here, parasitism and disease, predation and competition, well, these are all density dependent limiting factors. These are factors that change how much they're going to influence the population depending on how dense the population is. Just imagine if you have organisms clustered more closely together, there's a more dense population. With the pandemic that's going through our population right now, we try to keep ourselves distance, right? So if you're closer together, you're more likely to spread disease. If you're closer together, a predator can more easily catch those individuals and gobble them up. And there's going to be more competition if they're more densely packed together as well. But realize that weather patterns and natural disasters, it'll affect a population equally, whether it was a dense population or a sparse population. So we're getting that confirmation here. Density dependent are the ones on the left, competition, predation, and parasitism, and disease. And then the 2 on the right, unusual weather and natural disaster, the density independent factors. All right, so competition, one of the density dependent factors. Like I said, the more individuals, they use up the resources sooner. I think it's pretty self-explanatory. Individuals may compete for food, water, space, sunlight, shelter, mates, territories. All these are resources that individuals within a population would compete for. Now, this is an interesting historical record of moose population and wolf population on an island in, it's part of Canada, on the Pacific coast of Canada, not that high above the international border with the United States. And on this island, Isle Royale, let's see, I was almost thinking that wolves were introduced there, but they weren't. This is just a study keeping track of the populations of wolves and mooses and how they responded to each other. The bottom line on this, realize that what you'll need to be able to explain from this diagram is that the predator population usually is the one to respond to the changes in the prey population. So notice at a time when the moose population was really high, perhaps this red dot that I'm circling with my mouse. At that point, the moose population was really high, and that high number of prey individuals that the wolves can catch meant there's more food available for the wolves. And so when the population went high for the moose in that area right there, in response, the wolf population made a rise too. But then notice when the population of the moose declined rapidly, it may have been from a disease, it may have been from just the effect of the wolves preying on them so much because the wolf population went up. That's more mouths to feed on the wolf side, and that might have contributed largely to the moose population going down dramatically in that and quite rapidly as well. So bottom line, the predator population responds to changes in the prey population is the explanation you'll be expected to give for this. Herbivores and their effects. Right? Populations of herbivores and plants cycle up and down like populations of predators and prey. Parasitism and disease. Parasites and diseases can spread quickly through dense host populations. So again, a density-dependent factor. Stress from overcrowding can lead to lower birth rates, higher death rates, and higher emigration rates. Okay, moving on now to the density-independent factors. Regardless of whether it's a dense or a sparse population, these things will affect that land and make it uninhabitable, perhaps, at least for a limited time. So examples of density-independent factors include hurricanes, droughts, floods, and wildfires. They may actually vary with population density. All right, an overview of this. Take a moment and try to match these up yourself. Pause this video. All right, here are the answers. So if the two factors that are density independent are the ones that are more like natural disasters, flooding that covers the wildflowers, and wildfires that spread through a grassland. Both of them are density independent, and the two factors that are density dependent have to do with interaction between organisms. Non-native snakes released into a wetland, they prey on native rodents. That's density dependent. If the snakes are more dense, then they're going to make the population of rodents decline even more. And then secondly, flu virus spreading quickly in schools. That's very relevant today. We avoid dense quarters because we don't want to spread COVID-19. Chapter 5, Section 3, Human Population Growth. Our objectives here: discuss the trend of human population growth, explain why population growth rates differ in countries throughout the world, and our vocabulary terms here, demography and demographic transition. All right, so look at this transition that happened between photos taken in different ages. Industrialization, urbanization. These are two things that have occurred between the first photo and the second photo. This is a historical record of human population growth, and the key to this is there was very little change. It was really just logistic growth continuing on at a steady rate for many, many, many years. But then the Industrial Revolution changed things around and gave us the capacity to produce things much more rapidly, and the population started booming after that. When that's going to stop, a lot of people speculate. We don't have absolute certainty about how large the carrying capacity on the globe for humans actually is. But currently, if you look at the big picture, it's looking like exponential growth only. Coming up soon, many predict that we will see the population start leveling off, and it'll start looking more like logistic growth. Okay, this is showing us the 3 stages of demographic transition. Stage 1, early on in the change between a population that is dying off rapidly, they're making, let's see, death rate and birth rate are equally high. Stage 2, the death rate begins to fall, but birth rates remain high for a time. And stage 3, the population is really more of a modern society. The birth rate falls to meet the death rate. People in America, for example, don't reproduce nearly as much as in some other third world nations. Age structure, the one on the right is going to grow much more rapidly. I got to speed up. I only have about 10 seconds left. So it's much more stable. In fact, the population could even go down if it looks if it's more weighted on the top. And we'll have to